Hey everyone, welcome back to my channel Depth First. In this video, we are going to take a deep dive into the heap data structure, which is a complete binary tree that follows the heap property. We will be reviewing not just what it is, but how it's actually implemented under the hood. We'll be covering the following topics: complete versus incomplete binary trees, representation of a heap as a binary tree and as an array. What do we mean by the heap property? How to build a heap? How do we insert and delete elements into the heap? So this forms part 1 of the video series, and in part 2, I will walk you through how heaps are used in real life applications like heap sort and priority queue. So let's jump right into part 1 and start with complete versus incomplete binary trees. A complete binary tree is where every level, except possibly the last, is completely filled. And in the last level, all nodes are filled from left to right with no gaps in between. So let's check out some examples. This is a complete binary tree with 7 nodes. All levels are fully filled with no gaps and no missing children. This is a textbook definition of a complete binary tree. Here is another complete binary tree with 6 nodes. Notice the last level is filled from left to right. Even though node 3 doesn't have a right child, it is still valid. This one has just 4 nodes. The second level is full and the third level starts filling from the left, exactly how a complete binary tree should grow. An incomplete binary tree is one where a level other than the last is not fully filled, or the last level has gaps where nodes aren't filled from left to right. This tree is incomplete because node 2 has no children while node 3 does, and it breaks the left to right filling rule. This tree again breaks the left to right filling rule. This one is obviously incomplete because there is no left child of the root. And why is this concept of complete versus incomplete important? This concept matters because heaps are logically stored as arrays, but conceptually viewed as binary trees. Having a complete, predictable structure makes parent-child relationships easy to compute using simple math. And that leads straight into the next topic, representation of a heap as binary tree and array. Here is an array that logically represents a heap. Before we take a look at its tree view, let's first review 3 simple functions that will let us navigate the heap. Left of I takes the index I of the current node and returns the index of its left child as 2 times I plus 1. Right of I returns the index of its right child as 2 times I plus 2. Parent of I takes the index of the current node and returns the index of its parent. The first element in the array is always the root of the binary tree. If we apply these functions, the left child of node 8 is 4 and the right child is 3. Node 4's left and right children are 6 and 2, and 3's left child is 5 and right child is 7. And finally, node 6's left child is 1. The number above each node is the corresponding index in the array. But this isn't a valid heap yet because it doesn't follow what is known as the heap property. So let's try to understand what heap property means. There are 2 types of binary heaps, max heap and min heap, and both follow a rule called the heap property. In a max heap, the rule is that every parent has a value which is greater than or equal to its children. So the largest value is always at the top and the values get smaller as you go down the tree. In a min heap, it's the opposite. Every parent has a value that is less than or equal to its children. So the smallest value sits at the root and the values increase as you move down. If you are enjoying the content of this video, then please consider giving this video a thumbs up and subscribing to my channel. Do leave a comment if you have a feedback or a question. Your support encourages me to create more videos like this and help others as well. Thank you. Alright, so let's take a look at the tree we just built from the array, and I want to ensure that it is a max heap. This one isn't because it violates the max heap property. For example, node 4 is smaller than its left child, node 6, and node 3 is smaller than both of its children. So clearly this isn't a max heap yet. Now the big question is, how do we turn a random array into a proper max heap? In order to do that, let me introduce you to the concept first that given an element, how do we ensure that the element and its subtree below satisfy the heap property? Let's take node 4 for example. We want to ensure that node 4 and the entire subtree below it satisfy the max heap property. So we compare node 4 with its two children 6 and 2. Among the three, 6 is the largest. To maintain the max heap property, we swap 4 with the largest of the three, which is 6. Now 6 becomes the parent and 4 moves down to 6's original position. Next, we repeat the same process on the subtree rooted at node 4, which has now moved down. We compare it with its child 1. Since 4 is already greater than 1, no more swaps are needed. Let's run the same logic on node 3. Again, my point here is to convey that given an element, I want to ensure that the element and everything below it satisfies the max heap property. We compare node 3 with its two children 5 and 7. Among the three, 7 is the largest, so we swap 3 with 7. This process of bubbling the largest value to the top and then recursively fixing the subtree is called max Heapify. It is a key step in turning any binary tree into a valid max heap. Up next, we'll take a look at the code for max Heapify function, and then we'll see how to use it to build a max heap from an array. The max Heapify function takes the array and the index of the current node as a parameter. First, we calculate the indices of the left and right children using our helper functions left of I and right of I. We assume that the current node I is the largest among the three. That's why we initialize largest to I. Here we check if the left child exists and is greater than the current largest. If so, we update the largest to the left child. And here we check if the right child exists and is greater than the current largest. If so, we update the largest to the right child. If largest is not equal to I, we swap it with the largest and then recursively fix the subtree to maintain the heap property. Let's review the code for build max heap. We start from the last non-leaf node, which is at index length of array divided by 2 minus 1, and move backward to the root, calling max Heapify on each node. This ensures that every subtree gets fixed from the bottom up, and by the time we reach the top or the root, the entire array satisfies the max heap property. So how come length of array divided by 2 minus 1 is the last non-leaf node, and why do we want to start from here and move our way backward as opposed to going top down? Let me explain that to you in the next slide. Let's go back to the earlier slides where we figured out how to calculate the positions of left and right child nodes using array indices. This table here shows exactly where each child node would fall. Now, the node at index 3 has its left child at index 7, but the right child would be at index 8, which is out of bounds. And if you look at indices 4, 5, 6, and 7, all their child indices fall outside the array. This means that only indices 0 to 3 have at least one child. The rest, indices 4 through 7, are leaf nodes. They don't have any children. And that's why when we build a heap, we start heapifying from the last non-leaf node, which is at index length of array divided by 2 minus 1, or index 3, and work our way backward to the root to construct the max heap. Let's talk about the time and space complexity of max Heapify. Since a heap is a binary tree, its height is log of n, where n is the number of nodes. In the worst case, a node might need to move from the top to the bottom to restore the max heap property. So we might traverse up to log n levels. That's why the time complexity is O of log of n. The space complexity is O of log of n for the recursive call stack. Now let's talk about the time and space complexity of build max heap. At first glance, you might think that the time complexity of build max heap is O of n log n, since Heapify takes O of log of n and we call it on about half the nodes. But in reality, the total time is just O of n. And why is that? Because most nodes are near the bottom and require little to no work. Only a few nodes near the top take longer. So while the worst case time per node is O of log of n, the average work per node is much less, and the total work adds up to be linear time. Space complexity is O of log of n due to the recursive call stack of max Heapify. That brings us to the last topic, which is how to insert and delete elements in a heap. Let's say we want to insert a new element 10 into a max heap. We always insert the new element at the end of the array to keep the tree complete. This adds the node as the next available leaf in the left to right order. Then we bubble up, which means we keep comparing the newly added element with its parent while restoring the heap property. Let's review the code for this now. We'll start by adding the new element to the end of the heap. While I is greater than 0, we'll calculate the index of its parent. If the new element is greater than its parent, we swap them and move up to the parent's index. We repeat this until the heap property is restored, or we reach the root and then we stop. The time complexity is O of log of n because in the worst case, the newly inserted value might have to bubble all the way up to the root. The space complexity is O of 1 or constant since we are using an iterative approach and we do not allocate any extra memory. Deleting in a max heap means removing the topmost element, which is the maximum value. Since heaps are all about keeping the largest value at the top, we need to restore the heap after removing it. Let's review the code to see how that's done. We first check to see if heap is not none. After that, we grab the root element, and that's the max element, and we store it in a variable. Then we move the last element in the heap to the root position and remove the last element from the array. Now the heap property is likely broken, so we call max Heapify on the root to fix it. Finally, we return the original max element that we removed. The time complexity is O of log of n because after removing the root, the new root may need to bubble down to the bottom of the heap to restore the max heap property. The space complexity is also O of log of n for the call stack used by max Heapify. Python already comes with a built-in heap queue library that handles all the heavy lifting for you, from inserting and deleting to heapifying. But hopefully this video gave you a clear understanding of what's happening under the hood and how these core heap operations actually work. Thank you so much for taking the time to watch this video. I will see you in my next one. Goodbye.